Okay, so here's where we were last time. We were talking about moment of inertia. Again, this is not a physics class. The purpose of this example is not to teach you about physics, but physics here gives us a nice opportunity, kind of a nice excuse to do an interesting Riemann sum argument. So in particular, in a bunch of details I'm not going to repeat here. We already did them last time. But the big idea is we recognize that while this formula doesn't work on a whole mass that's rotating, because different parts of the mass are moving with different speeds, and which you can't just pick the fastest speed and apply it to pieces of mass that aren't moving that fast. It's no fair, right? So, but we recognize that if we break the problem up into little pieces, on each little piece we can apply the easy formula just fine, right? And then we take it from there, and arguments to be made, etc. Now, as it turns out, this gives a motivation for looking at a particular expression here. This thing here, we decide to call it I, because it therefore makes it clear the role that this expression is playing. Well, weird and perhaps counterintuitive, or let's say non-intuitive at least, that this expression would naturally be something. And yet here we are, look at that. That expression is the thing that's playing the role of mass, at least analogous to mass, right? In the angular kinetic energy formula that we end up with there. So how about that? Isn't that weird? So we give this thing a name because it is so natural in the algebra, the way the math worked out. It's called moment of inertia. So a good formula to remember, by the way, integral r squared dm. Beautiful thing about this formula is it works for any kind of situation. I did it here for a three-dimensional solid, right? But you could make an analogous argument for two-dimensional regions of mass, right? Whatever. So it's always going to be integral r squared dm, as it turns out. All of those arguments give the morally equivalent answer. So integral r squared dm is a great way to remember it. It's going to apply it at triple integrals, double integrals. We're going to soon see a kind of a single variable version of this in a weird way that's hard to anticipate. Okay, the big question, of course, is what is r? R is not, tragically, always the cylindrical r like it is in this example, because we are not always rotating around the z-axis, as I was in this first example. We could rotate around all sorts of different axes, and depending on what that axis is, right, various different options here for what the axis might be. The distance, the formula for distance to that axis. All distances, of course, to a line are understood to be perpendicular distances to that line. The formulas are going to be different in each case, right? So I strongly advise do not try to memorize a finite list of such formulas. There's too many cases. Axes, not axes, different directions they could be pointing. It's don't try to memorize your way out of this, right? Just notice that what the formula is usually a fairly straightforward question once you lay down the geometry, right? So, for example, if you've already decided that that's the line you're rotating around, and you want to know the generic formula for distance from some location x, y, z to that line, the geometry tells you that the nearest point on that line is that point that you can write down the coordinates of. Again, the geometry is critical. And then you can just write down what the distance is, and the distance is your r. Okay. So please view this as a geometry problem every time, and not as a long list to be memorized. It's just not a good strategy. Okay, so quick example, and then we're going to call it a chapter. Suppose I have this two-dimensional region here, right? And this two-dimensional region has mass distributed across it as per this formula right there, right? And so notice the mass density is not constant. It's more dense in some places. It's less dense in other places. That's weird, but let's just say, right? Then let's find the moment of inertia around the x-axis. Okay, here's the x-axis. right? And, good news. We have a pat formula for moment of inertia. Moment of inertia is integral r squared dm. Again, it's always integral r squared dm. Integral appropriate to the context. Here we have a two-dimensional domain, so this is, of course, a double integral over that domain. Everybody with me so far? And thus begins the geometry problem. We've got to figure out what r means in this case. Again, do not make the mistake of just, instantly interpreting r as being the polar coordinate. By the way, I will grant the criticism that, hey, maybe we shouldn't have used r for this. Yeah, I agree with that. Tragically, it's not up to me. This is a pretty standard notation. You're going to see this unfortunate notation elsewhere, so I feel obligated to expose you to this unfortunate notation. So anyway, heads up. Always, keep all that in mind. Okay, so what is this distance r? Again, the geometry problem begins from a generic point in my domain to my axis of rotation that's been established, the x-axis. Well, that distance, here it is. I can see it right there in the picture. It's y. So r becomes y. Everybody with me? Could have been concerned about the fact that, maybe it should be absolute value of y. After all, distances are always positive. There's no such thing as a negative distance, right? So, should I put absolute values around this to worry about that consideration? Well, in this case, I don't have to because y is always positive. Again, picture. So, no problem with that. But do be on the lookout. In some cases, you do have to worry about that, such as in this case up here. The line over there, you'll notice, is always sort of greater x coordinate than the generic point that we're looking at in our domain. And so if I were to write x minus a here, that would be always negative, right? And no good. So here you really do need the absolute values to make that make sense. Anyway, heads up. You always got to think about that. It's all downhill from here. Everything else should be familiar. Of course, mass is density times area. We have density right there. So density sticks in like that. And double integral. Bounds, outside in on the bounds, inside out on the evaluations. The rest of this I'm going to leave for y'all to crank out on your own. Questions? Yeah.
A little confused. So this is still in three-dimensional space.
Well, so the question as stated is arguably two-dimensional because the line is there, the region is here, it's all two-dimensional as described. Now, in order to make any sense out of why we would care about moment of inertia, I would need to talk about it rotating around the line, and that rotation would be in 3 dimensions, sure, right? But nevertheless, even if something is not rotating, moment of inertia is still defined. Just like if mass is not moving, mass is still defined, right? So this is a two-dimensional problem, but yeah, you're right that in order to make any sense out of it, we would have to at least imagine 3 dimensions. Yeah, good question. Anybody else? Okay. All right. That does it for Chapter 5. And on now to Chapter 6. We're going to talk about yet more kinds of integrals. Quick pause to take stock of how many kinds of integrals have we talked about to this point anyway. We've talked about, well, obviously long ago y'all learned about single variable integrals. Then we learned about double integrals. It was a new kind of a Riemann sum, right? Fundamentally different from a single variable integral. And then much discussion about how to compute double integrals, but the new Riemann sum, the new kind of integral itself, double integral. Then triple integral. And again, much discussion about how to compute triple integrals, change of variables, coordinate system iterated integrals. It's blah, blah, blah. But those are all different strategies for how to compute. What to this point we have seen as fundamentally 3 different kinds of integrals. Okay, so we're now about to add a 4th. We're going to talk about an integral on a weird domain like this. What does it mean to do an integral on a curve? Now, there's a temptation to look at this question and say, oh, okay, well, this is a two-dimensional question, so I guess I'll call this a double integral. But I point out that doesn't make any sense at all to call this a double integral. Double integral talks about breaking up your domain into little pieces of area. We don't have little pieces of area. There's no area on my domain at all. It's a curve. So double integral doesn't make any sense. It just doesn't fit. And then, of course, we say, okay, well, you've got little pieces of curve. Fine, let's call this a single variable integral. Well, our Riemann sum definition of a single variable integral is on an interval. Only on an interval. That's not what this is. So we just have a mismatch. This is not any of our fundamental kinds of integrals, and yet I can still talk about having some quantity that's distributed over a curve and wanting to chop it up into little pieces on which hopefully, presumably, the question at hand is easier to solve on the little pieces and then add up over the entire domain. I mean, chop it up, add it up still makes sense as a strategy. It's just not something I've seen before. This particular context is not something I've seen before. So, no problem. We just have to make a new kind of a Riemann sum. Here it is. This is our new kind of a Riemann sum. Notice I'm chopping up the little pieces and adding up and taking a limit to make round-off errors go away. That's all, familiar. What does all of this represent? What am I adding up? Well, on each one of these little pieces of curve, this little piece of curve right here, on that little piece of curve, I can talk about, well, on the one hand, what is the size of that piece of curve? How big is it? Well, that's length. Length is the notion of size, appropriate to a piece of curve. And then I can ask, well, what is it, what am I actually interested in on this piece of curve? If on this piece of curve I'm interested in computing mass, okay, well then I guess I better multiply lengths times mass per unit length. That would give me mass. Or if I'm interested in ant population, maybe I have a little wire hanging in space and there's ants crawling all over it and I want to count ants, right? Well, ants would be ants per unit length times length, right? But there's going to be one way or another some sort of quantity per unit length that I'll be multiplying by length to get whatever that quantity is that I will be adding up. So, so again, whenever you have stuff per unit size, I call that a density. By the way, it's not just me. This is generically called a density, stuff per unit size. So appropriate to the context, this is a density. Okay, how are we doing so far? Everybody, yeah, question?
How is this different from arc length?
Oh, because I'm not computing length. I'm computing, let's say, mass, for example. But now this delta S, right? The size of a piece of curve, yeah, totally. It's very much the same. Yep. Is that satisfying?
So like just mass distributed on there?
Yeah. Like, so for example, maybe this is a road, right? Maybe this curve represents a road, and I want to compute the total mass of concrete that it took to make the road. And the answer to how much mass of concrete did it take to make the road is not measured in miles. Right, it's just not a distance. It's fundamentally different. Yeah. But you are right that there is a connection in that arc length. Little pieces of arc length are going to be very relevant in answering whatever the question is. Yep.
How do you have mass if it's like a one dimension?
Right. No. Sure. So very often we model things in ways that are not physically quite accurate, but they're practically relevant. So, for example, my favorite sort of easy example, if you talk about chain, right? What does one do with a chain? Well, you stretch it across lengths, right? How much chain do you need? Nobody's going to tell you I need a certain certain volume of chain. You talk about length of chain, right? But it's three-dimensional. Well, yeah, okay, but I don't really care about two of those dimensions. I really only care about the length, right? So if you wanted to talk about two different kinds of chain, and one of them's thicker and heavier and the other one's less thick, less heavy, you wouldn't talk about the density of the metal itself. You'd talk about how much mass of chain per unit length, just because that's what you're actually interested in. Does that make sense?
Yeah.
Is okay for everybody? Yeah. So there's lots of circumstances where we model things by features that we actually care about, even if that's not physically real. Yeah. Okay. Good stuff. All right. So how are we going to denote this sort of an expression? I'll bet you can guess, aside from the fact that it's written here on the page. But we're going to kind of copy some old notational conventions, right? When you have a limit of a sum of a product that involves size, right? We use D's as a kind of a shorthand for the delta, whatever that is, right? So I'm going to use DS there, and an integral symbol to represent the summation. So there you go. And then, of course, I have to know what my actual domain is. And again, we make that a subscript, as we have in every other kind of integral that we've been talking about. So there's our notation. This is called a line integral. Specifically, I like to call this a scalar line integral. I like to distinguish this kind of line integral from a different one that we're going to see soon. Maybe not today. We'll see. But there is a fundamentally different kind of a line integral that will be coming along either today or next week. And I don't want to give away the game as to what that is, but fundamentally it's going to be distinguished by the fact that the differential here is a scalar. And the integrand here is a scalar. And you may be thinking to yourselves, well, of course it is. What else would it be? And that's going to be a little bit weird when we get to the next one, but they will not be scalars when we get to the next ones. Okay, but this one they are. So scalar line integral, and that's what that is. Now, bad news. When you find yourself looking at a scalar line integral, I mean, what have we actually got here? And the way I like to say this, you've heard me say it before, this is a strategy. This is nothing more than a strategy for how to compute. This is not a formula, right? I don't have a fundamental theorem of calculus for scalar line integrals, right? So are we going to break this up as an iterated integral? How are we going to actually get our hands on and chug and get down to an answer, to a number? I need a value that I can find on a ruler that I can cut. I need, practically speaking, to know an actual physical answer. How do we get that? And here's the approach we're going to take. I'm going to recognize that my domain here is what I like to call an undesirable domain. There our domain is. It's all curvy and bumpy and stuff. And this is undesirable in that I don't know how to chop it up. What have we done in the past when we have had undesirable domains? Well, we had different kinds of undesirable. We had domains that had corners, or domains that had weird curves as the boundaries, or that gave bad algebra, or there's various different motivations why we didn't like them. But what we did in the cases where we had undesirable domains is we viewed them as being images, right? We viewed them as being images of something else. How would I view a curve as an image? Well, I could talk about viewing it as an image of an interval. And in fact, not only can I do this, we have done this. Right? Viewing a curve as an image by way of a function of a range of values of t, that's a parameterization. So this isn't even a new construction. This, step one of, we have an undesirable domain. First thing we're going to do is view it as an image. Cool. Done. Old news. And then the next thing that we did when we were dealing with undesirable domains is we then did a pullback through that function by which our domain is an image. So view it as an image and pull back through that function. That function now being a parameterization. I'm going to say we're going to pull back through the parameterization. That's all it is. So we're basically going to do change of variables. It's morally equivalent to change of variables. The dimensions are a little different, so I can't use those old formulas, but it's morally the same thing as change of variables. And the details are wonderfully convenient. There's just not that much to it. I do know that I've got to recognize this ds here. That ds is not the same as this dt, right? When you do a pullback, the output size is different from the input size, and that's this whole stretching factor business. Well, that output size, ds, I already have, again, old news, I already have a relationship between it and the input size. ds is a distance, dt is a time. What's the relationship between distance and time? Speed. Right? So our stretching factor, the thing that we multiply by input size to get output size, the thing that we multiply by time to get distance, it's just speed. That's our stretching factor. How we doing? Everybody's happy? Boom. We're done basically. The pullback is dealt with. ds is magnitude of x prime times dt. Plug in the parameterization and off you go. We're in business. Let's see some examples. Real quick, before we get to the examples, this is just a point of formality that needs to get said. One could complain that wait a minute, your parameterization here, this, the formula that you use to parameterize a curve. Well, there's lots of different parameterizations. So, what, just use any parameterization? What if you use one parameterization and they use a different parameterization, and who's right? Well, good news. Turns out it doesn't matter. When you do pullbacks through parameterizations, these kinds of integrals, you'll always get the same answer for any parameterization. It doesn't matter. So go crazy. Parameterize however you like. Doesn't make any difference at all. So nice little bit of good news there. Okay, so example. Here is a physics problem. Several physics problems, actually, involving scalar line integrals. So we're going to have an irregular wire. So this is a piece of metal it's not a sheet of metal, it's not a line segment of metal, it's a curved, bent wire that is not only bent, but it's also got varying density. It's thicker in some places and thinner in other places. It's a weird, warped wire. And that said, and by the way, here's how it's warped. It's warped per that parameterization right there for these values of t. So now the lucky break will not always be so lucky, but here the parameterization is given. So again, we just wanted to kind of hit the ground running here with an easy one. Parameterization already given. In most cases, you'll have to find your own parameterization. But we've got everything we need to know about the wire, and now the question, compute the mass. We're also going to entertain the question of what's the location of the center of mass? And then also, what is the moment of inertia around the x-axis? So several questions that we want to know, and this is going to mean several integrals that we're going to have to compute here. All of them concern, of course, the same curve, the same wire, which is following the same curve with the same parameterization, the same bounds, the same density, the same object for all of these questions. And so what we're going to do is all going to concern some of the same parameters. Now we know from above here that we're going to have to pull back through this parameterization. We're going to be doing a pullback. We know that that's going to involve taking the derivative of our parameterization and computing its magnitude. That, after all, is our stretching factor. So we know that's coming. Why don't we go ahead and get that part out of the way? Because we know it's gonna be in all of our answers here. So I need to take my parameterization, take the derivative, take the magnitude, and here we go with that. The parameterization derivative, the magnitude, and so therefore this is my stretching factor. Whoops, let's get that whole. There we go. All right, everybody with me so far? All right, now, so armed, I'm going to actually answer all of these questions kind of at the same time. Rather than do one integral completely and then do the next integral and then do the next integral, it turns out we can kind of do all these questions in parallel as follows. First of all, let's talk Riemann sums. How do I compute mass? What is the chop it up, add it up strategy for computing mass? Well, the whole is the sum of the parts. The grand total mass is the sum of all the little pieces of mass. And, of course, mass, I don't like that color, mass is mass per unit length times length. Okay, let's see. How do I compute the x-coordinate of the centroid? Well, the x-coordinate of the centroid is old news, right, from last time. It's the weighted average of the x-coordinates. So Riemann sum is that. Another good formula to make sure you have memorized, right? Weighted average of the x-coordinates. And again, mass is density times size. Same as it was over here. Isn't that nice? Okay. Et cetera, et cetera. Computing the moment of inertia. Fine. Pat formula. Integral r squared dm. Again, gotta love it. It's always the same. Whether we're on a double integral or a triple integral or we see here a scalar line integral, always integral r squared dm, and this being a curve, where it's, of course, a line integral, not a triple integral. Okay. And again, mass is density times size, et cetera, et cetera. So, Riemann sum, you just write it down, and then mass is density times size. So the first part of this process for all four of these integrals is, it's a little different, of course, but it's, analogous. And then everything else really is very analogous. Let's proceed along. How do I compute ds? Well, stretching factor times dt. Here's the pullback. It's always the same because we're on the same curve. For all of these integrals, we're talking about the same curve, same parameterization, and therefore the same stretching factor, same pullback. And again, down here, ds is x. I tell you what I'm going to do. I'm going to see if I can fit all this onto one. There we go. Okay, so ds is x prime dt. Same x prime for all of these. All right. Everybody good? Yep.
X bar and y bar are the center of mass calculation?
Yes, that's right. Yep. All right. Let's see. And again, same parameterization. So don't forget your parameterization is literally telling you what are your x and your y. Right? Parameterizations tell you position, aka coordinates, as functions of time. So we have explicit formulas for x and y. So in these integrals, anywhere I see an x, let's see here. X is t. X is t. X is t. All the x's are t's because they're all on the same curve that all have the same parameterization. So again, coming down to here, further, x is t. X is t. And then likewise, y, you see, is t squared. So y is t squared. Y is t squared, etc., etc. Let's. There's a bunch of them to do. A lot of plugging in. And now I have four integrals that are all integrals on these are just single variable calculus integrals. And plug and chug, yeah.
Your A and B are 0 and 1.
Oh, yeah. Yet another thing they all have in common, all of these integrals are pulling back to the same interval on the t-axis, 0 to 1. And so these bounds, I should have made these all 0 to 1. Thanks for pointing that out. Yeah, I'll get that updated. These are all 0 to 1. Point being, they're all the same bounds because it's the same curve with the same parameterization. How are we doing? Is everybody happy? Okay. So this is the good news. It's you look at this question at the beginning, it's like, oh no, it's a fundamentally different kind of an integral. This is going to be hard. But it's really not. This is chop it up, add it up, computed through a pullback, which in fact summarizes very nicely with a very convenient little formula you can just remember, and it's all pretty plug and chug. Okay, let's see another example. This is a different example. So you're going to have to come up with a new parameterization, etc. Here I have a fence that's sitting on top of the unit circle. So here's my unit circle and the fence that's sitting on top of it. I'm going to forgive the poor art, but imagine a fence, like that. So the unit circle is the boundary of our property here that we're enclosing, and the fence is right on the boundary, of course, sticking up. Everybody see the physical layout there? Okay. What's weird about this fence is that the height is not constant. Right? I don't know if they really do that in the real world, but for whatever reason, we could imagine, like maybe I've got a vegetable garden over on one side and I want to make sure that it gets a lot of sun. Maybe I've got a chicken coop on the other side and I want to make sure it gets a lot of shade. I don't know. You could imagine that there might be a scenario where you want the fence height to vary depending on where on the property you're talking about. So here's my formula. Notice that the fence height gets bigger for larger values of x, and so I'm going to try to represent that on the picture here by doing something like that. Right? So now I've got my fence. It's a weird fence, to be fair, but I want to compute the area of this fence. By the way, pretty plausible story. If you're going to hire someone to paint your fence, you need to know how much paint you need, right? So more area, more paint. I guess you could, and by the way, don't forget to multiply by 2 at the end, right? But anyway, the area of the fence. Okay, so how are we going to compute this area? And I claim that what I've got is a scalar line integral. Now I'm going to skip over some of the algebra I just did. We'll come back to that momentarily. But here's my property line. Here's my property line. And here's the fence sticking up above that. Think of each one of these as a slat. Right? How would I represent area as we go along the property line? And the idea is, you can see right here, that I can talk about how much area there is on a slat. Picket, I guess it's a picket. Is that what they call it? And that area is, let's see here, switch to, so it's a little piece of length, ds, a little piece of length of our curve, times this height, whatever the height of the fence is at that location. So height times length gives me the area, and I just want to add that up now over the entire curve. And so adding up over the entire property line curve gives me a line integral. What do you think? Everybody see how the Riemann sum here kind of naturally arises as a scalar line integral. Okay, so, all right, in order to compute this thing, I'm going to need to parameterize my curve. Well, my curve here is a unit circle. It's easy to parameterize a unit circle. That's old news, right, hopefully. Everybody remembers how to parameterize the unit circle. I know I'm going to need to compute a derivative. I'm going to need specifically to have the magnitude of that derivative, aka the speed of this parameterization. This is lucky. I got lucky that speed is 1. How about that? Having the speed be 1 allows me very easily to rewrite my ds. My ds is x prime dt. X prime is 1, so it's just dt in this case. Everybody on board? Right. Okay. It's all plug and chug from here. We were given height. Height is that. How do I know how to rewrite height in terms of t? Again, don't forget the parameterization tells you your output coordinates, right? That is literally what a parameterization is. A parameterization is literally telling me here, for example, that wrong color. That x is cosine t. So when you want to do the plugging in part of the pullback, x is cosine t. Everybody all right? Single variable integral, plug and chug. I'm going to let y'all work out the details on that. Single variable calculus, the prerequisite trail of this course. Make sure that you're good with computing these kinds of integrals. This is a fairly easy one, but nevertheless, make sure you're good with single variable integrals. Okay. All right, so that's all I'm going to say about scalar line integrals. It's pretty straightforward stuff. I am going to try now to approach a seemingly similar question of chop it up, add it up over a curve, but where we're going to get something that's disturbingly different. So this, anyway, I don't want to give away the game, but let's proceed. Let's try to use a scalar line integral to this question to compute work. And so we're going to start at, let's see here, we're going to start at this point, and we're going to end at this point. And pick your favorite metaphor. Maybe we're driving along a mountain road, and along certain parts of the road it's uphill, along certain parts of the road it's downhill. Force dot displacement and all that. Or maybe it's a windy day, right? And this is a flat road, and because of the wind, it takes a certain amount of force to move yourself along the road at some points. Whatever. All right, so we do have this old formula, work is force dot displacement. This was an improvement of the old high school formula that y'all may have seen for work, which was just scalar, force as a scalar times distance as a scalar, which is fundamentally flawed. Displacements aren't scalars. They're intrinsically vectors. Forces are intrinsically vectors. Viewing them as scalars was unnatural. In a high school setting, maybe you don't know what a vector is, but anyway. But now that we are in a multivariable setting and vectors are on the table, this is by far a more natural way to understand work. It's a dot product of the intrinsically vector force with the intrinsically vector displacement. Okay, but even this has some problems. This assumes that our force is constant over the entire displacement. That's not always going to be the case. Look at this scenario here. Here I have force vectors that are very different depending on where you are. Not constant. That messes things up. This formula goes out the window at this point. Non-constant forces. Also, this formula here assumes that the displacement is over a straight line path like that, which is not what we're looking at here. Again, here we're talking about a particular curvy road, and it's not a straight path. So again, formula out the window. So this is we're in trouble here. We cannot use our old formula to compute work. We've got to figure out a new way to deal with this. And roughly speaking, what we're going to do is we're going to, again, having previous experience and successes looking at scalar line integrals, let's take this curve, let's chop it up into little pieces, let's add up the answers on each little piece. Seems like a reasonable approach. Notice on each little piece of curve, let's take this little piece of curve right there. That little piece of curve is approximately straight. Not exactly, but it's pretty close, and the limit, close enough, right? And let's look at the force vectors. Well, not exactly constant. Oh, whoops. Here we go. Not exactly constant. The vector there and the vector just a little bit over there might be a little different, but it's approximately constant. And again, in the limit, close enough. So on little pieces, looking at, one of these little pieces at a time, it's approximately a straight displacement with a constant force, and on there for each little piece, I can just say, force dot displacement, and then chop it up, add it up. And so strategically, we're starting to get a little optimistic. This looks like it's working well. How we doing? Everybody so far okay? Okay, here's the problem. One thing that I can see is this. I'm going to have to keep track of which direction I'm going. An easy case to make, let's see, let me go back to this mode, is that the amount of work it takes to drive up to Pikes Peak's top is greater than the amount of work it takes to drive down from the top down to the bottom. Right? Very, very different. This is a new aspect to the question. Let's go back over to here. Does it matter when I'm trying to figure out how much fence I have? Does it matter whether I paint clockwise or counterclockwise? No, not at all. Same amount of paint. Right? This is intrinsically not oriented. There is no direction that matters on this. If I had parametrized the other way, who cares? Right? Paint is paint. Likewise, mass is mass. Centroid is centroid. The direction that you do the addition makes no difference at all. Okay, not so here. So how we're going to deal with that is something we're going to have to start worrying about. And just to give a name to the issue, we're going to have to talk about a new concept called an orientation. And an orientation is just a notion of which direction is the direction that you're actually going on the curve. Right? So we're no longer going to talk about curves. We're going to talk about oriented curves for the kind of strategy that we're now developing for this new category of question. Oriented curve is essential because uphill is just not the same as downhill. How are we doing? Does everybody buy it? Is everybody happy with that problem? Okay. So right, fine. Well, on each little piece of curve, now this is the easy part. We've already kind of talked through this. On that little piece of curve, how much work does it take to move along that one little piece of curve? Okay, well, there's my dx vector. My, my linear differential approximation of my displacement along that piece of curve. So there's my displacement, and there's going to be a field vector. Force vector that I'm going to dot that with. No problem. F dot dx. Right? This tells me how much work it takes to move along that one little piece of curve. And if I then want to add up over the entire curve, well, there you go. That kind of looks like a scalar line integral. Kind of. There's an eyebrow-raising aspect of this, but adding up over the entire curve, this is what we would write down, sort of thinking that this ought to work. Does that make sense to everybody? And of course, now we do have to recognize, though, that this is pretty different, right? This is not a scalar line integral. Check it out. We've got here a differential that is fundamentally a vector, and this is not an accident. This is not an oops on our part. It is fundamentally a vector. Displacement here is fundamentally a vector. That's in recognition of the fact that going one way is different from going the other way. It has to be a vector. And then likewise, our integrand, the force, it's a vector. No longer a scalar. So, we have to give this a different name. The book uses the same convention that I like to use here. Call this a vector line integral. out of recognition of the fact that it's fundamentally a different thing from a scalar line integral. Everybody okay with that? Okay. Alrighty. Good news. We already know how to deal with the objects in play here. So I'm going to just kind of remind you that we've already developed all of this stuff. We did this back in chapter 3. I forget which section number. I want to say, oh gosh, let me just not. Anyway, somewhere in chapter 3, and we developed this idea of the dx vector and the velocity and the related notion of the unit tangent vector and how all of these objects are related to each other. All of this is old news back in chapter 3. And so I'm just going to pull this up, right? Pull this out of our toolbox, and then I can rewrite this vector line integral that we were looking at. All right? And I can say, okay, well, let's see, I already know that dx is x prime dt. Fine. Boom. X prime dt, plug that in, have myself a different formula for my vector line integral. Which, by the way, is a wonderful formula. Look at this. Everything in this expression is in terms of t. So, pull back, already done. Right? I've effectively parametrized and effectively pulled back through the parameterization to get this integral now from a to b. Sweet. Now, alternatively, this is just sort of a different way you can think about this. Don't forget, we also already established that dx is the unit tangent vector t times our size differential ds. And I can do that replacement here. Replace dx with t ds. That gives me then a different alternative formula for a vector line integral. This is a pro-con thing. What are we going to do with this formula here? Why do I like this formula? Well, there are some situations where this is actually useful. There are some situations where the unit tangent vector naturally presents itself in the context of the question. And sometimes good things happen just by making quick, easy observations about that unit tangent vector. So this is a good formula to know for that reason. Also, this formula, as it turns out, naturally connects to some other kinds of questions that are going to arise that we haven't talked about yet. So for future use, future interpretations, it's useful for that reason as well. And the last thing I'm going to say about this formula is notice it kind of looks like a scalar line integral, doesn't it? Integral, blah, 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 ds. Feels like it looks like a scalar line integral. I consider this to be a bug, not a feature. After all, this is fundamentally different from a scalar line integral. It's a different critter. I don't think it's a good thing that two things that are actually importantly, fundamentally different are, look alike, aka are easily confused. I don't think it's a good thing. I think it's a bad thing. Right? So I do warn you against that. I think the book agrees with me on this point. The book has a strong preference, it seems, in their notational choices to write it more like this and less like this. So I'm glad that we're on the same page there. Be warned, though, there are a lot of textbooks that like this notation. So no problem. It's just notation. But just realize when you see this, first of all, what they mean is this. And be warned that even though this looks like a scalar line integral, it's not. It's a vector line integral, and that matters. Okay. All right. Okay, and that's just ran out of time, so let's draw the line right there. Don't forget, we have a test on Friday. So good luck studying. See y'all on Friday. Good luck to everybody.